It just came out, Jason. You can see the placenta all over the damn bison. This is amazing. It's the miracle of birth. Up on all fours for the first time. Whoa. While we were just driving by, we noticed the herd was near the fence. We came over to see what was going on, and there was a baby. It was just born, and just moments ago stood for the first time.
You have to forgive my enthusiasm. When we were planning our trip to Fermilab, America's premier particle accelerator, I wasn't exactly expecting to run into a herd of bison. This is a national research facility where they smash particles together at near light speed. But once you drive through the gates at Fermilab, you're immediately confronted by visually striking architecture and a menagerie of sculptures, and apparently newly born calf taking its first steps. This odd juxtaposition is somewhat by design. When Fermilab was established in the late 1960s, its director, Robert Wilson, wanted to position it as a facility that was operating at the frontier of scientific discovery. To ensure that metaphor was lost on no one, he worked to transform the lab's newly acquired 6,800 acres in the suburbs of Chicago into a quintessential American prairie, replete with farmhouses, tall grasses, and an increasing bison population. Wilson, a veteran of the Manhattan Project, wanted to change the image of physics research from the secrecy and barbed wire fences of Los Alamos to something open and free and accessible, where the goals were neither military nor commercial, but simply to further our understanding of reality. And so, as one academic put it, he literally built a scientific utopia in order to build a scientific utopia.
There's something really cool about this being a place where we study the constituent parts of reality to the best of our knowledge. And here, we're seeing the moment of birth. The best part is they said that they would name the bison after me. And yeah, it's an honor.
In this episode, we'll meet some of the people working at the frontiers of high-energy particle physics. But it's not really explanations of how all this stuff works that I'm most interested in. What I want is to better understand the personal motivations and philosophies of the people doing this work, and to talk to them about humanity's eternal search for meaning and purpose in our vast, miraculously complicated, rapidly expanding, and incomparably mysterious cosmos. This is Dispatches from the Well. Chicago has a rich history of messing around with the constituent parts of matter. It was here at the University of Chicago that a group of scientists led by Enrico Fermi created the first controlled, self-sustaining nuclear reaction. The rest is history. Today, I've come here to find out what kind of people turn up on a rainy Saturday morning for a lecture on particle physics.
Good morning, everyone. Welcome back. It's great to see you. Next year, I'm going to be a postdoc in Notre Dame there. So I was driving around to see where I might want to live. And of course, I was also visiting the university, and they asked me to give a talk about my work on Thursday. So I just can't stop talking about physics, but I wouldn't want to.
It turns out that it's not University of Chicago students. But this group, which includes retired teachers, artists, machinists, and even local church leaders, are students just the same. They're here seeking answers to some of life's biggest mysteries.
The big questions that we want to ask is, how did we go from this homogeneous, uniform, hot, dense plasma to what we see today? Yes.
And when postdoc fellow Seth Korn ends his hour-long lecture, people are far from ready to leave.
How do they say that the farther one are moving faster?
I certainly appreciate that this is a difficult sort of thing to get your mind around.
And even though Seth fields a litany of questions from the audience, they're still hungry for more.
That was my question.
Yeah, so the point is, again, that we have this expansion of the universe. So if the universe were static, then indeed...
The sentence is actually saying that the galaxies have a mass that is larger than...
There's something really familiar about being in a room like this. I grew up attending a really small church. I can remember sitting in rooms not so much bigger than this one, where someone was up front at the lectern giving a speech about the mysterious attributes of the universe, and afterwards people would descend on the presenter and try to get some additional insights, or at times offer their own.
Indeed.
So it's pretty inspiring to see people with the same sort of zeal, but applied here to things like the behavior of subatomic particles of the earliest moments of the universe. But what is it they're hoping to find out? Are they trying to understand quantum mechanics, or are they looking for something deeper? Fermilab's first director, Robert Wilson, was no stranger to the idea that efforts to unlock the mysteries of the material world could impact humanity in a profound way. In 1969, he told a visiting documentary crew the following.
The main application of the work here is spiritual, if you will. It's because in a philosophical sense, in the tradition of Democritus, we feel we have to understand, in the simplest terms, what matter is. In order to understand who we are, we must understand what we are. And we would expect that that would be the practical application, that everybody has a desire to know the answers to these very simple fundamental questions, and we can satisfy that curiosity of man.
There's a lot about the landscape here that's really interesting, like these ridges in the earth where you can imagine the tunnels are for the particles to be run through. Oh, there it is. Very formidable building. It kind of looks like something out of a sci-fi movie.
Fermilab's mission is to uncover the mysteries of matter, energy, space, and time. We use enormous particle accelerators to send subatomic particles hurtling into targets at nearly the speed of light, and we build gigantic particle detectors to study the properties of those particles.
Particle accelerators are essentially high-tech racetracks for slamming protons and neutrons into targets like carbon and metal in order to flush out even smaller particles that are normally hidden from view. Then they study those particles, and they do this over and over again, rinse and repeat. Now, I fully get that the people at Fermilab, they do pure science. I mean, if you look at the experiments that they're involved in, read the press releases, or watch the videos they produce, they're heavily technical. There's not a lot of emotional language there. But I'm curious about how their work makes them feel about the world around them. It has to influence the way they think about their own sense of meaning and purpose, right? For my own part, I think trying to explore the smallest parts of matter is pretty amazing and mind-bending. And I suspect some of the people at Fermilab are thinking the same thing, and I'm intent on finding out. Where better to start than at the top? Bonnie Flemming is Fermilab's Deputy Director of Science.
I'm a little bit in awe. The space is really
Beautiful.
cool. Where are we standing? What is this building?
We're in the Fermilab atrium of the high rise. We call it the high rise. And it is where many scientists and engineers and the mission support side of the lab work.
So there are a number of particle accelerators. Where does Fermilab sort of sit in the hierarchy?
Well, in the US, we are the center of US particle physics. We are the Fermilab National Accelerator Laboratory. So the high energy physics that we do that's based on US soil is done here.
So you all are studying protons here and the various parts of the proton.
We're studying the building blocks of matter. Proton is one part of that. Quarks make up the proton, and there's 6 quarks, which are 6 of the 12 building blocks of matter. There's another 6 building blocks, which include the electron family, let's say, including the neutrinos. And it's those 12 building blocks of matter and how they talk to each other that we're studying.
What Bonnie's talking about here, together with the force carrier particles like photons, gluons, and bosons, is what's known as the Standard Model. It is our, quote, current best theory to describe the building blocks of the universe, which is to say, in another sense, that it is somewhat subject to change. Scientists here at Fermilab are constantly looking for subatomic particles that may complicate our picture of the universe, that don't seem to follow the rules.
Can you talk to me a little bit about some of the discoveries that have been made here over the years?
Absolutely. The top quark was discovered here. That was hugely important. It helped us finalize the 6 quarks that constitute half of our 12 building blocks of matter. The tau neutrino was discovered here. That's the third of the 3 neutrinos that, again, help solidify our understanding of the building blocks of matter. We knew it was there, by the way.
When you say you knew it was there, is that because we had the standard model and it sort of predicted that these other things would be there?
Yes, we had a theory for the standard model that predicted a certain class of particles, and we'd seen in detectors all of them except the tau neutrino.
These predictions Bonnie is talking about essentially come down to basic mathematics. After a series of particle collisions in the 1970s, scientists noticed that some energy had basically gone missing. They could not account for it. This suggested the existence of previously unknown particles. But it was only through years of subatomic detective work that scientists were finally able to balance the books, so to speak.
So right now we're walking through the accelerator directorate on our way to where it all starts, which literally is a can of hydrogen that has protons that you spray across an accelerated gap. So they start from velocity 0 and are accelerated up to near the speed of light. The protons start there at the proton source. And they travel through the LINAC, the linear accelerator, which is along this hallway. And that's below grade, and beam is running, so it's in a running tunnel. Right now, the beam starts in there, basically. Hard to see it, but it starts in the beginning of the LINAC tunnel.
Are you all running experiments, like 24/7?
Absolutely.
Yeah, interesting.
When the beam is on, the experiments are on.
Okay.
What would be the point?
Yeah.
So these are all the support equipment that we need to be able to power the LINAC, so the LINAC can accelerate particles on the first of their path around the particle accelerator complex to get to near the speed of light.
I'd love for you to talk a little bit about the diversity of research that takes place at a place like Fermilab.
There's lots of different ways you can do particle physics. By the energy frontier, the highest energy beams, by the intensity frontier, very intense beams where you use things like neutrinos and muons to probe the standard model, by cosmic experiments where you look up at the sky in a variety of different ways to figure out the myriad of things we don't know about the universe, including dark energy and dark matter, and the 4% of the universe that is described by the standard model, relatively small compared to all the stuff that we don't know. And therefore, things at the smallest scales and things at the biggest scales across the universe.
I think a lot about my daughter, and for her, like I know more than anyone else in the universe. She has an expectation that I can answer all of the questions. And when I give her I don't know, there's profound dissatisfaction. And sometimes it seems like she's a little disappointed, and it's just, her perspective seems to be just use your phone. It'll tell you what's going on. And there's a sense in which a lot of science education in public school, when I think back on my own experience, was the dissemination of information. Like, here's all the things that we know about the world. And the fact that this is a body of knowledge that is constantly evolving, that there are things that will be challenged and overturned and new things that we will learn. It may have been something that was said, but it certainly didn't feel that way, given the kind of rote way that my education happened.
I know exactly what you're talking about. When you take a physics class, Intro Physics 101 in college, you're solving problems that were solved a long time ago, and you're reading it from a book that's maybe even on its 5th edition or 10th edition. And you have to learn, in my case, the language of physics to be able to do physics. But we have to be able to not just tell young people and the public in general how little we know or how many open questions there are out there, but also teach them as early as possible about what it really means to be a scientist. A scientist is not answering questions in a book where the questions are already solved. It's much different than that. Research is, there's no manual. You have to go into a lab and figure out what to do. And my own education felt very rote until I started doing research and I realized, oh, nobody knows the answers to all these questions and nobody even knows how to answer them. You have to make it up as you go. And that's what inspired me to be a scientist.
Yeah, I mean, that sounds like an invitation to do something.
Yes, there's a whole bunch of stuff to do and it's really interesting and we make it up as we go in a positive way. But what you're trying to do is answer the unanswered questions, and there's a ton of them.
Go big or go home might be Fermilab's intellectual motto. Our focus is on the big, unanswered questions of science. Questions like, why is there something rather than nothing?
Don Lincoln is a senior scientist at Fermilab. He's also host of hundreds of Fermilab YouTube videos on everything from dark matter to quantum foam.
Atoms, like the ones you see here, make up all of ordinary matter.
He's also part of the team that discovered the Higgs boson, the last missing piece of the Standard Model. Since Fermilab sits on 6,800 acres of mostly empty farmland, I thought there must be a good place here for some stargazing. So I dragged Don and my new unistellar telescope out to a structure known as the Proton Pagoda.
Don, thank you so much for agreeing to come up here to actually do a little bit of stargazing.
Yeah.
Maybe you could tell me a little bit more about the facility. You're kind of the face of the place in a lot of respects. You're like the guy who I know from YouTube.
So here I am in the middle of outer space.
Has anyone ever drug you up here to do stargazing before?
Not up here, no.
What is this facility?
Well, this particular facility used to be the control room for our beamlines. So the original accelerator would accelerate the beam in a circle and then shoot it out like a sling to a number of targets. And this would control the beam. So now it's just sort of a pretty architectural feature.
Yeah.
And maybe archaeological too, because it's pretty old.
All right, I'm gonna get this can out before it gets too dark and I can't actually manipulate it. Ugh. Don, I wonder if you could talk to me, considering we're messing with the telescope here,
Sure.
about the connection between astronomy and particle physics.
You know, the connections between astronomy, particle physics, and in the astronomical things, mostly cosmology, is truly profound. Because what we do here in colliding our beams together, we are actually able to recreate the conditions of the universe a very small fraction of a second after the Big Bang. So we're essentially understanding, you know, how the whole thing came to be. We can't do that out there. We can see what the Big Bang has turned into. But here, we can really turn back the clock and see what it was like right after it happened.
One of the frameworks that may help us understand the behavior of particles in the early universe is quantum mechanics. Quantum theory is notoriously difficult to wrap your head around. Even Nobel laureate Richard Feynman, a pioneer in the field, had this to say.
There was a time when the newspapers said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. On the other hand, I think I can safely say that nobody understands quantum mechanics.
I talked to Doa Churchuola, a theoretical physicist working in quantum here at Fermilab.
Do you feel like anyone really understands quantum mechanics?
You don't understand quantum mechanics, you just get used to it. And then that's what's actually kind of happening to me.
Were you always interested in math?
Yes.
Yeah.
I actually first wanted to be a mathematician. However, I decided not to do that because if you do something wrong in mathematics, you are stupid. If you do something wrong in physics, you can say that my theory did not agree with the experiment. I'm going to think more.
So talk to me about just a conventional day for you here. What do you do exactly? What does it look like?
Since I'm a theoretician, first I try to solve some equations on pen and paper for a physical phenomena that I'm trying to solve. And then try to see if the pen and paper calculations match with the actual toy model that I'm creating on computer.
What do you think that means? The fact that mathematics can so accurately represent the world around us. It just feels so kind of tangible and absolute. It's purely conceptual.
Well, that means basically mathematics is a language to understand the nature. I mean, I don't know what else to say about this, because I don't want to go into really philosophical discussions.
But you get to see and think about all of the really unusual elements of reality on a regular basis. I'm curious about how it makes you see the world.
I mean, it is really kind of difficult question to answer. I mean,
but do you think that the work that you do gives you a different kind of appreciation for the mystery of all there is? Or at some point, is it just, it's work, it's a job? I'm curious about it.
I really don't know how to answer that. So,
no?
Yeah, no.
Okay. All right, I think we got to run.
Thank you.
Thank you so much for your time.
Thank you.
I appreciate you.
Doe's obviously a little uncomfortable with this line of inquiry. I mean, I'm not a physicist, so I can't help but think about some of this stuff from a different point of view. Considering the Accelerator Lab's long-standing embrace of art and design, I thought maybe an artist might be more on my wavelength. Ricardo Mondragon is Fermilab's artist in residence, and he's a sculptor who transforms the harmonies found in the universe into physical matter.
I feel that art and science is just a matter of perspective. You can talk about color in the sense of a painting, but if you go deep enough, it becomes a science. My dad studied a postdoctorate in molecular biology.
Okay.
And he works with electromagnetic fields. So part of some waveform generators I have in my studio, my dad has in his studio. So that was sort of an early introduction to physics.
What about physics is most intriguing to you?
For me, I think physics is the closest we've ever been to understand a little bit whatever we can understand of the universe.
It's kind of interesting. I mean, you have the universe, where you have all of this energy, these waves. Eventually you end up at matter.
Exactly.
And then the matter starts walking around, thinking thoughts.
Exactly.
And making art about waves and music.
It's sort of like the scientist. It's like a bunch of cells looking at each other in the microscope. It's just sort of a reflection.
It's kind of wild.
It is.
See, you get it. I get it. Sometimes when I talk to some of the researchers, it's like, yeah, isn't that wild? Isn't it weird? Yeah.
It's just so normal to them.
Yeah.
I can understand how proximity to the extraordinary can actually make something seem a lot less unusual. But Rachel Pfaff comes to particle physics from a totally different angle. She actually started out shoveling walks here at Fermilab, and now works as a technician in the neutrino division. For her, being part of the science here is still a thrill, with one small exception.
Rachel, do you have anything that you need to,
I have a meeting at 2, but it's a Zoom meeting, so I don't want to go anyway. Okay. I mean, I'll be honest. Does anyone want to go to those?
No.
Okay, I was going to turn it on and work while it was on and hope that they didn't call my name.
How do you describe your job to people when you meet them?
It would depend, if I wanted to impress someone or if I wanted to just play it down. So if I wanted to play it down, I'd be like, it's kind of like Homer Simpson, but with a particle accelerator. And then if I wanted to impress someone, I'd be like, well, I drive a particle accelerator, you know?
Is this something that you would have ever expected 15 odd years ago?
Absolutely not. Yeah, I certainly didn't plan this career path.
Yeah.
It just sort of happened. I had been past the control room before, when I would shovel the walks. And so when I applied, I just went there and I was like, hey, I want to work with you guys. And I guess that left a good impression and they decided to hire me. And
yeah.
It's such a cool job in operations because you get to learn all about the accelerator, the whole complex, the experiments, just how things work here. And so it gives you this really cool overview. And it's also like being in school again. And sometimes I'm have to watch a YouTube video to figure out what I'm doing, you know? But it's nice because I don't know if it's just working in science, but there's this feeling that everyone's working together. And so if you don't understand something, someone else will be like, oh, you could do it this way, you know? And everyone's just trying to figure it out.
So there's a real sense in which all of the work that you've done here it's the stuff that makes all of this research even possible, Do you ever think about the role that you're playing in this research that's happening?
I mean, sometimes I do.
Yeah.
Knowing that, I'm putting my hands on stuff that this accelerated beam goes through, I really just like being part of it. I can look back and say, okay, I'm not like the physicist or whatever, but I was part of this huge experiment that all these people from all over the world are part of. That's pretty cool. I can feel good about that.
Yeah.
I was building and turning wrenches while I was pregnant with my daughter. And then so I got before and after pictures, me pregnant with the modulator, and then I brought my daughter in and took her picture with the modulator. And then I did the same thing for both my sons.
You find it at all strange, such an extraordinary effort being made to study what might be the smallest bits of everything there is?
It is crazy that you have to do something so big to understand something so small.
Yeah.
And I don't know.
Unimaginably small.
When I talked to my dad about it, he was like, those particles are all just pretend. It's
Is he joking or is he serious?
I don't know, that's the thing with the old guy. But it is hard to, it's you can't see it, you can't point at it, but yeah, you have to do this whole effort just to prove that this stuff exists. I don't know, I think it's cool though. I mean, someday, maybe 50 years from now, we'll understand things about the world that we didn't understand before. And it'll be a direct result of the stuff we're doing here.
One of Fermilab's projects that may change the way we see the world is called DUNE, or Deep Underground Neutrino Experiment.
DUNE is a best-in-class neutrino experiment that's addressing some of the most fundamental questions in particle physics, and I would say physics today.
Neutrinos, first discovered in 1956, are nearly massless particles. Trillions of these things are passing through your body every second, leaving no trace because they so rarely interact with other matter. That is how small they are. And when DUNE comes online in 2028, Fermilab scientists will fire neutrinos from Batavia, Illinois through more than 800 miles of rock towards a detector in South Dakota. The goal is to figure out if neutrinos are part of the reason that matter exists, or why there is something rather than nothing.
Something happened in the early universe, so we ended up with a tiny little bit extra matter, some asymmetry, which is good because that's what we're made of. Us, all the stars, everything we see in the universe that's comprised of standard model particles is the matter-dominated universe. We don't know what happened in the early universe to cause us to live in this matter-dominated universe. But DUNE is a project that will address, in short, I really like to say it, are neutrinos the reason we exist? I've been talking about this project and involved in this project for a long time. And every time I talk about it, I get really excited about it because it's sort of astonishing to talk about these huge, really hard things that we're doing. And we're doing them. We're building the experiment to be able to uncover the mysteries of the neutrino and therefore, we hope, the mysteries of the universe.
Yeah, I get a very clear sense of the extraordinary effort that goes into a project like this, and all of it being directed at answering these really fundamental questions that, in a way, humans have always wrestled with. Has your perspective on the universe broadly, on kind of the nature of the big questions that we ask and why we ask them, has that changed much at all?
It has, in the sense that I am more humbled than I ever have been. I think about what a tiny speck we are in space and in time and how little we know, and I become quite humbled. And I feel lucky that I can work with people here, people in the international community, to build huge projects that can try to help us understand a little bit more about the universe.
What about the role of physics in terms of the way it interacts with philosophy broadly? Is there a role to be played there?
I think our job here is the physics side. And maybe that first of all, that's what we're supported for. And for me, that's sort of the way I think. I talked before about asking, are neutrinos the reason we exist? That's a very fundamental question. If I ask more philosophically about, why neutrinos are the reason we exist, I feel like that's out of my purview. I hope that's not a disappointing answer.
No, it's not at all. No. Do you have to make a choice with respect to questions that are that big as to whether that is going to be something that inspires you to keep going, or it's kind of depressing and disheartening in some respects because you know that there'll always be another question?
Oh, it's never disheartening.
Okay.
It's true. You answer one question and you create many more. I've never found it disheartening. It's the opposite. I find it inspiring. Maybe it's daunting, but it's always daunting in an inspiring way. There's always more to learn, and the important thing is to think of the next right question to be able to advance down the road.
But federally funded multi-billion-dollar projects like Dune aren't the only way to better understand our place in the vast, mysterious cosmos. You can get a long way with good company and a quality telescope, at least when the clouds aren't conspiring against you.
So in order to get this thing going, the first thing I have to do is find a star, which I just finally acquired one.
Yeah.
And it's orienting.
It's extraordinary that we just see the one.
Yeah. We got the thing set up. We're going to see what we can see.
Yeah,
and it's already starting to. Yeah, there's a couple of extra stars on it. Great. Well, Don, I'm curious. When did you first know that you were going to become a scientist, and did you have any sensibility about what kind of scientific investigation you wanted to do at that point?
Hey, like most kids, I was going to be a paleontologist.
Okay.
Because dinosaurs are just freaking cool.
They are very cool.
But then I really started getting interested in these existential questions, these big questions, the questions of life and death and creation and the universe. And by the time I was a teenager or so, I was really sort of hooked on physics because they were really mind-blowing things. I mean, quantum mechanics in special relativity. And then I started learning about things like the Big Bang and things. And so these really big, bizarre questions hooked me. And there was no question I was going to do science.
Do those same questions still drive you today?
Yes.
Yeah.
Oh, God, I wouldn't do this if I wasn't still fascinated by precisely those questions. I would love to know the answers.
Has your work informed your perspective?
I mean, I'm a scientist because I was interested in what you call the existential questions, the big questions that were originally theological and then philosophical, but are now becoming scientific.
Well, this is interesting, Don. One of the things I've been most interested in is talking to people like yourself who work on these big questions about the way their perspectives have been informed by the work that they do. And some of your colleagues are less inclined to talk about this kind of stuff than others.
Yes, of course. Well, they want to be taken seriously as scientists, don't speculate. But I can tell you, I grew up open-minded about such things, which is why I did study philosophy and theology and so forth in college. I have minor degrees in those. But as time went on, I became disenchanted. What I've grown to understand is the importance of skepticism and confirmation, because it's very easy to have an idea, and it's very easy to find something that validates your idea. And you're the easiest person to fool. So the hard thing, and this drives people around me, friends, nuts, that I don't believe something right off the bat. I have to sort of show that it's true from several different directions. So the scientific method is really been important for me. I mean, not just in science, but in all things. Because when I believe something, I want to have a reason to believe it, not just because it feels good. And now I have to be critical. Because, well, for one thing, what you learn dealing with other scientists is if you're not critical, they will be. So you don't want to look like a fool in front of them. When you show them something, you want to be right.
Is there still room for awe and wonder?
Oh, certainly.
Yeah?
Certainly. I am constantly amazed by the fact that we're here. I mean, the universe didn't have to be this way. I mean, it could have been the laws of nature. It didn't allow for atoms, didn't allow for us. Stars could have burned too fast, and then we wouldn't exist. I mean, it's amazing that everything we see has to work just right for us to be here. If matter didn't exist, we wouldn't exist. So it kind of has to be true that because we're in a universe that we're in, the laws have to allow for us to exist. But nonetheless, the intricacies of how this all happens. Carl Sagan's famous "we're all star stuff." I mean, we are the debris of stars that lived and died billions of years ago. There's a certain majesty in that.
But then there's also like the Stephen Hawking quote about us just kind of being chemical scum, which I suspect he was trying to allude to the kind of vastness of the cosmos and get us away from an anthropocentric perspective. But at the same time, there's just a little less romance in that sentiment than I'd like.
Yes, it's true. If you're really cynical, humanity is not crucial to the universe. If Earth disappeared tomorrow, the universe would continue, other stars would burn, galaxies would form. We are not the center of true creation. We're the center of our creation, and that's important to us. But in that sense, I would agree with Hawking. I suspect that the universe is full of life. In fact, I think I could argue reasonably well that life exists out there. Intelligent life is probably rare, but it must exist. And so out there somewhere, there's other eyes or something similar looking at us and probably asking exactly the same questions.
Yeah, well, I suppose until then we kind of keep looking up, keep contemplating, keep finding reasons to be amazed by the happy coincidence that we are here, whether or not we're able to figure out exactly why we're here.
Yeah, I think it's important that everybody should once in a while go out and look up at a clear midnight sky and wonder.
A little clearer than tonight.
But we see the moon, and the moon is pretty too.
Yeah, and I'm grateful for the company and the conversation. So thank you very much, Don.
Well, I've had a wonderful time. Thank you.
There's something kind of seductive about particle physics. The idea that there are still so many mysteries surrounding something as fundamental as physical matter. The very stuff that makes up you and me, and it's kind of wild. It's no wonder that over the past 100-some years, scientists have devoted so much energy to solving those mysteries. And one day, those answers may help us to fully understand how our universe came to be. But it may not get us any closer to understanding why it came to be. And what I've come to realize is that that is probably okay.
We hauled the telescope out, brought it all the way to Chicago. As it turns out, it's quite a bit of cloud cover tonight. What I'm really grateful for is the fact that so many people are determined to keep searching for answers to really daunting questions that have always been of great importance. Who are we? Where are we going? What are all the things made of? And why can't I find a clear sky to use this telescope? Okay, cool, yeah. Take it off the stand.